Okay, our final section in our first chapter. This is going to talk about infinite geometric series. Very, very important. I very briefly mentioned, a series called the Taylor series, I think in section 1.3, and how it has uses. You might be wondering, what's the point? Okay, that's what I'm interested in. What's the point of studying something that's infinite? And it turns out that there's a very, very good application for infinite geometric series or any kind of series that we consider to infinity. And one of the things that you're going to have to wrap your head around is that infinite geometric series, okay, can actually converge to a finite number. Okay, so you can have a series that goes on for infinity, but that will actually converge to a finite number, or it will diverge and continue to grow very, very large or very, very small in the negatives. Okay, so this slide goes through some of the applications to this. Okay, so read through that, and of course there's massive applications to this in pure mathematics. Okay, so we're gonna be dealing with pretty much an unapplied area right now. But I talked about converging and diverging. It all depends on your value of r. Okay, that common ratio. If the common ratio is between -1 and 1, you probably actually recognize that they behave in certain ways. If it's between -1 and 1, okay, so for example 0.5, then it will converge, and will converge the sum of an infinite. Okay, the sign means infinity. Okay, an infinite geometric series will converge according to this formula. And I derived the formula up here from our formula in section 1.4. Essentially, when n grows very, very large, and if r is less than 1 or between -1 and 1, this term will become 0, and that will leave you with this. Okay, so if it's bigger than 1, or if it's less than -1, it will diverge. So, only a few examples. Again, I'll do A, and I'll give you the solution to B. It says determine whether each infinite geometric series will converge or diverge. Calculate the sum if it does exist. Okay, well, first of all, here's the series, right? T1 is 1. What is r? It all depends on what r is. If r is bigger than 1, or if it's less than -1, this will diverge and we're done. Okay, so when we calculate what r is, in this first example, what are we left with here? In this first example, 1 divided by 5, okay, divided by 1 is just the following. So, unfortunately, it will, in this situation, it's going to converge. I'm going to put this into a decimal form for us, okay? Unfortunately or fortunately, it depends what your application is, right? So this will actually converge into numbers. Check it out. Check it out. 1 plus 1 over 5 plus 1 over 2, 5, and so on. What will this converge to? Well, what's our formula? Our formula is, okay, and we're actually looking for S. We're looking for the sum. Sn is T1 over 1 minus r. Very simple, right? So that is the following. Okay, that's it. You compute that, you get 1.25, which should make sense, because if you look at this, it has to be bigger than 1. So right off the start, you get 1.2. Okay, and right from there, it's going to keep slowly creeping toward this value, and it will never exceed it. At infinity, it will equal this. Okay, this next sequence is divergent, and this next series, I should say, sorry, because r here is 2, right? So on a quiz or an exam, if you get a sequence that is divergent, simply put this right there. Okay. Now this is a really cool example. This is how we're going to finish off the chapter. You can actually use series to essentially convert decimals like this, okay, that have a repeating decimal, into a fraction form, which can be very useful actually. So if you have 0.584, this whole term repeats, so you're going to have the following over here, 584, 584, 584. You can actually express this as such. You can express this as a series. So let's determine the sum of this, okay? And it has to exist actually because this number is present when we convert it to a series format. R will always be in between -1 and 1. So when you compute this, what do we get? Now, this is going to be a writing nightmare here for me on this little writing pad, but I'll do my best. R is going to be the following. Um, 0.000584 divided by 0.584. You're always going to get an R value when you convert these things with a 1, okay, because by the nature of the division. This is clearly less than 1, it's clearly greater than -1. So this exists. T1 here is 0.584. So we simply plug it into the formula. So Sn is equal to T1, 0.584, over 1 minus R. This equals 0.584, and this, if you pull out a calculator, which I'll do in a second, is the following. We didn't need a calculator. Now, I'm not going to leave it like this. I'm actually going to multiply both terms by 1,000. Then you can reduce from here. It just so happens that you won't be able to reduce this fraction. Okay, so there's no common multiples in either of them. No common factors in either the numerator or denominator. So if you type this into your calculator, which I did right here, you're going to get back this. So that's how you can go between the two. If you have this right here, you actually can work backwards. Okay, you can divide both by 1,000, depending on this number, how big that is. And then you can go and you can easily figure out R, and then you can generate the sequence or the series. Okay, so that is the chapter. Make sure you try the practice problems. Once you finish the practice problems, you can move on to the assignment. Okay, the assignment 1, A1. Finish that, submit that. Then try the little practice quiz to get used to either writing with a stylist, like I'm doing right now, and you can take a bit of practice, and then you can attempt the Chapter 1 exam.